Hello to everyone. My name is Alex Stankovic and I come from KTH Royal Institute of Technology, which is based in Stockholm, Sweden. Today I would like to tell you something about some results on approximability of minimum sum vertex cover. Let us begin. First, we will recall familiar minimum vertex cover problem, and as an input we are given a graph, and the goal is really to find the smallest vertex subset which covers all the edges of the graph. As a variant of this problem, we have a problem of interest, namely the min sum vertex cover problem. This problem was introduced by Feige, Lovas and Tetali in 2004, and as an input we again have a graph, and now the goal is to visit vertices and minimize cover time of edges. What do I mean by this? Well, let's say we visit this vertex first, then we cover 4 edges at time t, and we will add 4 times 1 to the cover time. Then we can visit this vertex, we cover 4 more edges, so we add 4 times 2 to the cover time, and let's say we visit this vertex third time, and then we visit 3 new edges, and we add 3 times 3 to the total cover time. Then we can continue this procedure, and in the end we will get the sum to be 49 if you trust my calculations. Okay, so this has been well studied problem, and we have certain approximability results. In particular, in the paper of Feige, Lovas and Tetali, a 2 approximation algorithm has been shown. And this is really very different from the 2 approximation algorithm from the vertex cover problem. And in particular, as an evidence to this, we also have a algorithm of Barinholtz, Feige and Peleg, which show that you can do it better than 2 approximation. And this has been substantially improved in a recent paper of Bansal, Batra, Farhadi and Tetali, who give 16/9 approximation algorithm for this problem. Let me just mention that all of these results really rely on the linear programming techniques. Also, Feige, Lovas and Tetali give certain evidence that minimum sum vertex cover may be easier on regular graphs. In particular, they show that the greedy achieves 4/3 approximation ratio, and also using semi-definite programming, we can do a slightly better than 4/3, namely by some small unspecified constant epsilon. Next, I would like to mention certain inapproximability results. In particular, we have 1 plus delta NP hardness approximation in the paper of Feige, Lovas and Tetali, and here delta is again some very small unspecified constant. And also we have 16/9 linear programming integrality gap by Bansal, Batra, Farhadi and Tetali, and basically what this means is that their algorithm that relies on rounding the natural LP relaxation is tight. Their analysis of the LP is tight. Now in this paper we would like to add certain results to all this list of results the minimum sum vertex cover. So, what we prove is the following. First, we show that assuming the unique games conjecture, minimum sum vertex cover is NP hard to approximate within 1.014. Also, hardness reduction outputs regular graphs for which approximation might be easier, and this in turn makes our hardness reduction result even stronger. We also improve approximation algorithm on regular graphs, and we show that minimum sum vertex cover can be approximated within 1.225 on regular graphs. Our algorithm basically uses the same framework as the Feige, Lovas and Tetali, and we introduce some changes to the already existing algorithm. First, we sharpen certain quantitative bounds used in that paper, and secondly, the algorithm from the Feige, Lovas and Tetali paper relies on so-called max KVC problem, and we pretty much use almost optimal approximation algorithm for max KVC problem, which are known today and were not known back then. Let me mention that I will not discuss theorem 2 anymore, and I will only focus on the theorem 1 from now on. I would like now to touch on some proof ideas that go into inapproximability. Our starting point is a unique games instance I, and the unique games conjecture states that it's NP hard to decide whether I has low value, which is known as the soundness case, or high value, which is known as a completeness case. And very interestingly, completeness is more challenging case in this work, while usually in pretty much almost every single work on hardness approximation, most technical work goes into soundness, and I think that this is an interesting difference. Tell you a bit about soundness case. Basically, the graphs output by our reduction belong to the same family of graphs as those that appeared in the optimal hardness result for max cut, namely the breakthrough result of Cott, Kindler, Mussel, and O'Donnell. Since this is a very well-studied family, we already know that they satisfy certain properties as shown by Austin, Cott, and Safra, and this property is slightly more explicitly stated by Austin and me. In particular, if the starting unique games instance has low value, then given every vertex subset of the graph output by the reduction, well, the subgraph induced on this subset is dense in certain sense. So what do I precisely mean? Well, if I let R to be the fractional size of the set S, then we have the following. The edges, the total number of edges with both endpoints in S divided by the total number of edges is at least gamma rho of R minus some lower order terms, where gamma has to do with the cumulative density function of bivariate Gaussians, and rho is certain parameter of the reduction that belongs between -1 and 0. Now the question is, how do we use this? And well, let's consider any ordering of vertices and let Ui be all but first I vertices in this ordering. Now, some VC cost is going to be shown as this sum written on the screen. And why is this the case? Well, let me convince you in that. Consider an edge covered at time t. Well, it has two endpoints. One of them is chosen at time t, other one is chosen later. So in particular, the edge will be charged t times in this sum. When I goes from 0 all the way up to t minus 1, it's going to be charged exactly once for each summand in that range. So that edge will have cost t, and we will include all the other edges here. So now, using the soundness property and rewriting the expression above, we have the following inequality up to some lower order terms. And now this sum is well approximated by the integral shown on the right side. So in conclusion, if the value is low, then minimum sum vertex cover is at least the size of the edge set times the integral between 0 to 1 of gamma rho r dr. Now let me briefly discuss completeness case. In this case, we are actually required to use affine unique games instance I, which is an interesting property of our reduction, since I really haven't seen many papers that really need this structure of the affine unique games in the completeness case, or in general at all. Luckily, affine unique games are equivalent to the unique games, so we don't really need to use any stronger conjectures. What is the affine unique games instance? Well, we need an instance of particular form that is equivalent to the unique games instance, and it looks as this. We have m equations, and every equation looks like xi minus xj is equal to the some constant ck, where both the variables xi, xj, and the constant belong to some fq, and q is a certain fixed constant uniform across the whole instance. And since we are working with a completeness case, we actually do have an assignment to, let's say, assignment z to variables, which satisfies almost all of the equations. Now, take any constant s and consider an assignment zs, which is basically z translated by s. Well, this assignment actually satisfies almost all equations as well, right? Because every equation has like subtraction, so the s will cancel each other, it will get cancelled out. So in particular, this really helps us describe helps us find a good ordering, because it helps us describe the space of all the solutions of these unique games. And in this case, the sum vertex cover is at most 1 divided by 3 minus rho. So then putting things together, we actually have that the completeness and soundness implied in approximability of 3 minus rho divided by the integral from 0 to 1 in gamma rho of r dr. Now choosing r rho to be minus 0.52 will give us the hardness stated in the beginning of this talk. And I would actually like to conclude with certain open questions. So in particular, one of the open questions I have is that whether can we actually use the semi-definite programming approach for non-regular minimum sum vertex cover? I think this would be a very interesting venue to explore. And also a good question is to see if we can post-process our hard instances output by the reduction and maybe make them irregular, and hopefully this will improve hardness, because I do believe that it's possible that the minimum sum vertex cover is actually harder on the non-regular instances. With this, I would like to conclude my talk.